Okay, so just for the record, if something is moving in circle or part of circle, that means there is a force acting towards the center of the circle. And to use Newton's second law, you need to identify, you need to figure out what that force is. Okay, once you do that, you can use that. Okay, so here is one such example. In this video clip here, oh, hold on. Can you wait? So you see there is a coin sitting there, and to help us to visualize, there is a thread. Okay, there is a thread, and now it's sitting there. As long as this is spinning not very fast, what happens? It goes in circle. Once it starts spinning faster, what happens? It slides. And which way does it slide? You want to take a look, okay? Which way it moves. And then after it reaches to the, let's say, corner somehow at some point, then what does it do? Does it fly off like that or goes sideways? Okay. So pay attention to that. And as long as it is going in circle, that means there must be a force acting towards the center of the circle. What that force might be. Think about that one as well. Okay. I spotted this coin over here, okay, right now. And right before that, where was it? Here. I want to see it right after this there. So it's here at this point. Now that point is there, but where this thing was, it has gone there. So it looks like it's flying that way with respect to that line, right? And every time we spot before this, what happens? It is right on top of that string, right on top of that string. Looks like my circle wasn't perfect. As you can see, until this time here, in the timeline, the coin went in circle. It stayed on the circle. And, oh, not just that, but even after that, okay? So it was in basically in that circle there, right? And after this or something like this, so yeah, so it kind of started moving away from that initial circle. Now it is moving directly away. So that's what we see when we closely look at or observe the, frames, different frames of this video. So now, Here it was going in circle. So what was the force making it go in a circle? If something is in circle, what does it mean? There must be a force acting towards the center of the circle, right? So what was that force? The string is, this coin is not tied to the string, so it's not a tension. We're not talking about tension. The string is there for so that we can see, oh, it's always following that string, okay? So it's not tied to the string. So what force is acting towards the center? Can you guys type that on the chat? Now I have different window for the chat, different screen for the chat. So that way, and now I can see what you guys are doing, okay? So I see friction, static friction, centripetal, normal, okay? And kind of repeating them, okay? Good to see that. So now let's look at the possibilities here. Centripetal force. Centripetal is just a name because it's pointing towards the center. So centripetal force can be any. Normal can be centripetal, friction can be centripetal, gravitational can be centripetal, okay? So centripetal simply means it's just pointing towards the center, that's it. It does not a specific force. So maybe using centripetal force is not a good idea here, okay? So now, other force, I see normal. So this coin is sitting there on the surface there, flat surface, right? So normal force means it must be pointing up there. But we are talking about the one that's pointing towards the center. So normal force doesn't look like a good choice here either, okay? So it's a friction force, okay? So it's the friction force, and as long as it is not sliding, that means it's a static friction force, yes, okay? So now here is question, exact same question here. So it says, okay, the record is rotating at this speed. Oh, what is that? RPM. What does RPM means, folks?
Rotation per minute?
Revolutions
rotation
per minute?
Yeah, rotation per minute or revolution per minute. Yeah, revolution per minute sounds better here for us. But yes, rotation per minute is also good. So that is actually angular speed. But we learned that angular speed has to have unit of radian per second. But this thing is in revolution per minute. So we need to take care of that, okay? Before we can use this in formula. And friction coefficient is given there. How far? So that's not friction force, but it's a friction coefficient. So from friction coefficient, we can write friction force. We know Fs is mu s, I should say Fs max. So right before it starts sliding, that's the maximum. The friction force becomes maximum there, right? Mu s times n. So that means by giving this, somehow it's trying to give us friction force. We need to figure out how much friction force is there. So now the question is, how far from the center of the record can the coin be placed without having it slip off? So we are looking for value of r, radius of the circle, okay? So how far it is from the center? Is it here or here or here? Okay, so that's what we want. Is this done here? Looks like certain things are done. So it looks like we need to use free body diagram. Why? Because it's talking about r, radius. Radius of the circle is in the acceleration equation. So acceleration and force, they are related by Newton's law. So that's how I know we need to use Newton's law. Okay, so that's that. Oh, here, free body diagram. So normal force pointing up, weight is pointing down, and static friction force is pointing towards the center of the circle. So if this is going in that like this, then it's pointing towards the center of the circle. So for the circular motion, to use Newton's second law, it's convenient if you choose positive towards the center of the circle, no matter where it is. If we choose towards the center, you don't have to, but it's convenient. That's what I'm saying. Okay, so I think that's what I'm going to be doing. So now, what's the net force? And remember, this net force is towards the center, and there is only one force acting towards the center. So that's why I can just write Fs, and that is equal to mass times angular acceleration, sorry, radial acceleration. So that means it's a v square over r, or omega squared times r. So in this case, it's the omega that's a given, not v. That's why we are using this one. Okay, so m times that. So that's why you see that. Okay. So now we don't know how much friction force is, but we know friction force is related to friction coefficient, and friction coefficient is given. So that's what I'm doing here. So it means I can replace that Fs by that one there. Oh, I did not replace yet, but I will. And now here we need normal force, and normal force is equal to mg in this case. It's only the normal force that's balancing the mg. Those are the only forces along the vertical reduction. Another way to write it, n minus mg is equal to 0, means n equal to mg. So yes, before I can replace that, I can replace this n here, because I don't know n either. Let's write mg. We know g. M is not here. But usually in this kind of situation, mass cancels. So that's why you do not want to just try plugging in number at the beginning. You don't plug number at the beginning. So, oh, you're looking for mass. I don't know mass. I cannot solve this problem. That may be your conclusion. Okay. If you try to plug in numbers right away. So that's why I'm not plugging in here. Okay. So now, with this, the Fs becomes mu s times m times g, right? So that means this gonna be same as this, and you can see this equal to that means m in both sides means the m cancels. Okay, so now we are looking for r, so let's solve for r, right? So r is just mu s times g over omega square. So this problem is solved, but there is one little problem inside this big problem. We need to convert this revolution per minute to the radian per second. So revolution and radian, how are they related? One revolution, 360 degree, or 2 pi radian. So we can replace revolution by 2 pi. Okay, so that's what I'm showing you here, how to do it. Okay, so I start by writing revolution per minute, and I am now replacing revolution by 2 pi so that I can cancel revolution, and minute by 60 seconds so that minute can be canceled. Okay, so with this, I can come up with this number here. That's going to be radian per second. And now I have everything I need, okay? So it says 0.08 meters means 8 centimeters. Okay, so that's how we use Newton's second law. So we are using Newton's second law for the circular motion where centripetal force was friction force. Okay, centripetal force was friction force. Radial force was friction force. Okay, so now let's watch another video. And here, this is cylindrical object that spins. And after certain speed, this floor drops. And there can be sound here. Let's see. So yes, there is sound. And kids are on the ride, so they are excited. And sometimes they get afraid and start, let's say, screaming. And mom, parents, they are taking video here, okay? And so they are excited too. So let's watch and listen. And while doing that, now also pay attention. So this kid is moving in a circle. So there must be a force acting towards the center of the circle. So what is that force? And when floor drops, this person is not coming down, stuck in the wall there. So what force is keeping this person there? Okay, what force is countering the gravitational force? Think about that while watching this, okay?
I'm gonna puke just looking at this.
No, we're good!
It's the oxygen! Abby, don't move your arms, trust me. It's what's about to throw up!
Izzy, are you okay?
It's okay. I'm taking a video. It's even better. It's okay. That's what's supposed to happen.
Okay. See, gravitational force is still there, right? But what force is keeping this kid there? What is balancing the gravitational force? So I see normal force, I see static friction force in the chat, okay? So two possibilities. So normal force, which way normal force acts? Let's think about that. So there is this wall, that's where this kid is. So normal force is actually acting perpendicular to the surface, means that's going to be the normal force in this case. And how about friction? Let's see. So gravitational force is trying to pull this kid down. So this kid is trying to slide down, not sliding. Oh, yeah, so that looks like that's a friction force, static friction force, okay? Yes, that makes sense. So now with that, we have a free body diagram, do we? Yeah, looks like we have free body diagram, okay? Do we? Okay, go ahead. Then you have a minute. So it's the same situation, okay? It's the same situation. So what is the free body diagram here? A minute. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do. Ha. A, B, C, D, E, F, G. Okay, so we got almost all of them, right? All of them. But we mostly got A. Hey, it sounds like, for me, it feels like B makes sense. Let's say I'm thinking B as the correct answer. Why am I right or wrong, folks?
B doesn't show any force pulling her towards the center of the barrel.
Oh, and there has to be force towards the center of that cylinder barrel, right? Oh. And what keeping this kid stuck on the wall then?
That would be the static friction force.
Right, so that's preventing from falling down when floor is that. So yeah, so that's static friction force. Static friction force. Up force is static friction force. And this is mg, I know that. Mg, I know that. Static friction force, I know that. This is normal force we talked about, right? Do we see any source of this force, by the way? Is something pushing this kid to the wall? Is wall is pulling this kid somehow? If you go close to the wall, does wall starts pulling you inward?
Doesn't it kind of depend on where your center of gravity is, though? If you're facing outward, then I don't know. Never mind.
You mean if you are on this side of the wall, then that could be the, but yeah, no, wall is behind the kid, right?
Yeah.
So yeah, I think that's not a good idea. Yeah, we don't see the source of this force, right?
Yeah.
But we know this is normal, that, so yeah, the A makes more sense than B. So I'll go with B, just like many of you did, okay? So yes, it is not easy question, but we always need to look for the source of forces. And what forces we know? Let me repeat that one more time. Contact force, that comes through the contact, like a normal force, friction force, right? And could be sometimes tension if we attach string, right? So those are the contact forces. And there can be non-contact, long-range force, that is gravitational force. Those are the kind of force we know. If we have to somehow, come up with the another mysterious force, probably we're not doing it right, okay? So let's think in terms of that, okay? So again, this is exactly same problem, the barrel problem, right? So what's the difference here? So R is given. I think I don't even need to do, let's say write them down here. So now the question is, what should be the minimum angular speed? So that means we are looking for V or omega. Omega, right? Okay. So by the way, you can type on the chat when I ask question. For example, you could have just typed omega, and I can see those now easily because I have now separated screen for the chat. Okay. So anyway, so that's that. And those. So what's the free body diagram here? And what are we looking for? Omega. Yes, we already talked about that. So let's make a free body diagram. I don't need to draw that. So let's replace the rider by a dot. and mg always going to be vertically down, friction force that. And if it is going in circle like this, then that's going to be the normal force, right? So these are the forces. So now let's assign the axis. So axis, we can say x, or for the circular motion, it acts towards the radius of the circle. So we may also say r. Okay, we may say r. You may see r written in book. If that happens, it's just another way of noting down the axis, and we can keep this as a y, positive y. Okay, so now what's the Newton's second law for the circular motion? Radial. See, that's why this r helps. Okay, is mass times a radial, just ar or a rad. That's that. So how many forces are acting towards the radial direction? And what is that? And what's the sign? Towards the radial direction means in this direction, how many forces are acting? Just one, that's right. Okay, and that's the normal force. And what would be the sign? Positive or negative? Positive. That's right, because that's what we chose, positive. We choose positive towards the center for the circular motion, okay? And mass and radial, and again, angular speed we are looking for. So that means the formula we should be using is just like we did for the coin, okay? Omega squared times r. Okay, so that's left-hand side, just one equation, right? So now normal force. So friction coefficient is given and we need normal. So how do I find normal? Normal and friction force. Is there a relationship between friction and normal force? So in this case, static friction. See, the person is not moving, still stuck trying to move, means it's going to be static friction force, right? So normal and static friction force, they are related through this equation here, mu s times n. And I'm sorry, I'm confusing you guys by writing uppercase and lowercase, switching those for the normal. Here I wrote uppercase n. It means normal, okay? So now, mu s is known, but we don't know fs. What do? Usually we use mu s to find fs, mu s and n normal to find it. Here we are looking for normal. So what do? For that, we need to go back and look at the free body diagram. Do we see what friction force is in the free body diagram? At least what equals friction force? Hey, I see a lot of mg. Yes, OMG, it's mg. Okay, so that means Fs is in this case equal to mg. Means normal force is mg over mu s. Now I can come back to this equation and use that. Mg over mu s is m omega squared times r. See, mass cancels. And we are looking for omega, means we need to move this r from this side to that side. Oh, it's in numerator, so it's going to go into denominator. So g over mu s times r is omega squared. So omega going to be under the square root of this. So g we know, mu s is given, r is given. So that means we know omega, and the unit of omega going to be radian per second in this case. Hey, now you can design a rotor. So you can do this, and then you calculate how fast you have to be moving before you start dropping the floor. If you start dropping floor too early, then the person gonna just come down with the floor. So you have to be going at least a certain speed before you can start dropping the floor. And that's what this speed is, okay? And to be in safe side, you wanna go faster than this before you start dropping the floor. So now, what does it mean when we say mass cancels? So let's say a parent and a kid both decided to ride on that rotor ride. So parent has a larger mass, kid has a smaller mass. Do we need to worry about the difference in speed because of the mass? It is telling us, oh, we don't have to. Whether the parent is a football player who has like 300 pounds or normal, not so athletic parent, for all, what happens? It's the same. So that's what it cancels means. See, in mathematics, we say, okay, it cancels. In physics, we need to think, what does that cancel means, right? And that's what it means. We don't need to worry about mass of the person or the rider, okay? Okay. Now, let's go for the ride. Another kind of ride, in this time, it's car ride, not the rotor ride, okay? So that means it's gonna be V, not omega, okay? So when we turn, we may not, pay much attention, but when we are turning, what happens? There is a force acting. If the force is not there, then we cannot turn. So for example, you are driving in a road and that road happens to be a bit icy and you are going fast. You try to turn, what happens? You keep going straight. You cannot turn. Why can't you turn? Because to turn, you need a force towards the center. And the force has to be acting on the car. Force has to be acting on the car wheel. Not on the steering wheel. The force on the steering wheel not gonna bring the car, okay? And so it's the friction force that makes car rolling, that helps car to turn, okay? So it's like a coin, okay? It's like a coin. Situation is like just a coin on the there, okay? And so we can think of this as a part of circle. Let's say that's the circle, and model that as a circular motion. So the speed is going that way, and friction force is acting towards the center. And this friction force is static friction force, okay? Remember, the car is trying to skid. So if there is no enough friction force, what happens? Car doesn't roll, rather skid. So we are talking about that static friction force that keeps, okay? And when we are walking on the road, it's the static friction force that helps us to, move forward. So we can solve problem like this. So it is basically same coin problem. It's the coin problem, okay? So we can make free body diagram. In coin problem, there was a friction force towards the center, weight of the car, and normal force, assuming the road is flat, okay? The road can be a bit inclined, and we'll talk about that pretty soon, okay? And that's the force. So this is now basically the same problem we had for the coin spinning on the, that platform, Okay, so that's Newton's second law. And there is only one force, and let's choose the axis this as a positive R and say this is positive. So that way, since the direction of force and acceleration are always in the same direction, radial acceleration, that way we don't have to keep writing positive or negative sign for this. Okay, so that's the easy thing, you know, that's the convenience of choosing positive towards the center. Okay, so now again we need friction force from the friction coefficient. So what do we do? Oh, before we do that, we can solve for B first because we are looking for B, right? And replace Fs by mu s times n. So it's done, right? So and again we need n, and if we look at free body diagram, n is mg, so that means mu s times mg. And once we plug that in this equation, what happens? Let me actually write that down. So now V square, so I am going from here to here, R times Fs. What is Fs? Mu s times n. What is n? mg. So that means it's mu s times mg. Divide that by, see there is m still there. So again, it does not depend on mass, so we don't need to worry about whether it's a car or big truck. Okay, so the speed is gonna be same. So you don't need different speed limit for car and the truck on the road, okay, for the turn. And you cannot go this fast when there is, let's say, something on the road. Road is wet. When road is wet, value of mu s becomes less than, let's say, 0.4. So the speed becomes less as well, okay? And so on. So this is V square. So to get V, you need to take a square root, okay? And when there is ice, what happens? Mu s becomes really tiny. So that means you need to be crawling rather than actually driving car. You have to be crawling when you are icing road, okay? That's the reason. Okay, so now if there is no friction, what do you do? If friction is not enough and you want to go faster, what do? You make the road a bit hard, what we call banked road, okay? As you can see here. So in this kind of situation, this would be flat road, but road is tilted, banked. So this angle of banking is this, right? So I can redraw that. So for a moment, let's say there is no friction. Or let's say very little friction. And what the speed, right? So yes, of course, there's gonna be friction, always friction. So we can include friction. And when we include friction and this banking, what happens? Things get a little bit complicated. So that's why we like to talk separately. If necessary, we can combine it. But for this course, you don't need to combine both of them, at least mathematically. Yeah, in your mind, you can do it, right? Okay, so we can replace that car by a dot to make free body diagram. But for now, let's just keep that as that car. And what happens? It's going in this circle now. Means there must be a force pointing in that direction, and that's the force we are looking for. Okay, that's the force we are looking for. So where is that force coming from? Nothing is pulling this car this way, right? So there is no tension force or something like that. But we know when something is in this certain plane, inclined plane, there is normal force. There is force of gravity, right? Those forces are there. And there can be friction, but here we are not using friction. We are assuming friction is negligible. So the weight is always vertically down, and normal is always normal to the plane. Are there any other forces acting on the car? I don't see it once we neglect the friction. And by the way, if there is friction, then what would be the situation? So in this case, the car is, so in this case, what happens in this incline, basically the friction gonna be acting this way here. The static friction I am talking about, okay? That's how, remember how when it's flat, it acts towards the center, but it's gonna be inclined. So now, to use Newton's law, we need to find component of that one in that direction, if we were to include friction, but we are not including that. So that's that. So based on this, and why am I choosing this one axis in that direction? We always want that in the direction of center of the circular path, okay? So when we had inclined plane, we chose axis, one of the axes along the inclined plane. But that was the case when object was actually moving along the axis, the incline. Do you guys remember that? So we chose that when object was actually moving along the incline. Here it's not moving along the incline. These cars are not sliding up and down on the incline, are they? They are not. So that's why that axis is irrelevant. But what is relevant? What we need is we need total force, net force towards the center. Whenever we have circular motion, we need net force towards the center. So that's why we choose one axis in that direction and try to find force or component of force in that direction. The mg is vertical, so that means it's not going to have component in that direction. But normal is going to have component, okay? But we know this angle, banking angle, means we know this angle. We have used this in previously in our free body diagrams. So now normal is over there, so we want this angle somewhere there. So which
That would be
so this
adjacent.
So if we have line crossing like this, and if we know this angle, means we know this angle. Those angles are going to be same, right?
Cosine, sine.
So we know this angle now, means this is n. So this, if we go this way and that way, so force acting towards the center gonna be the opposite or adjacent?
Opposite.
Opposite, right? So that means it's gonna be n sine theta. And this is gonna be n cosine theta. Okay. So that's how we make free body diagram for this banked card. Once we have free body diagram, net force is this, that is equal to mv square over r. Okay, the same thing. So radial force is the component of that normal force. Okay. Oh, they are already written there. So I'm moving to next slide to make room, but basically it's the same problem with some numbers, okay? The same thing. So we were there. So normal force was there. And which angle was known, this or that? That, right? And that means, oops. That means this is n sine theta. And this is n cosine theta. Once we have that, we can forget about n. Right? So now we have along the radial direction, there is only one force. And we are choosing this as a positive, means n sine theta is positive. M and AR is V square over R. Remember, this acceleration is centripetal acceleration as well, radial acceleration. It points towards the same direction as a force. So that's why we don't need to worry about signs here when we have just one force and and acceleration there, okay? So that's that. So we are looking for speed. R is known. Theta is known. Mass is not known, and let's hope it gets canceled, right? So it looks like we need normal force. Okay, so where do we find normal force from? So for that, we go to the vertical component, and along the vertical direction, it's not accelerating. That means n cosine theta minus mg is 0. Or you can see directly, and you could have written just this. You could have just written this, okay, by just looking at the free body diagram. Okay. So now we have n over here. So let's solve for n, mg over cosine theta. Hey, normal force in this case is mg over cosine theta. Normal force is not always mg. Sometimes it can be OMG. Okay, so now let's come back here and plug in n. So what is n? mg over cosine theta. So instead of n, I'm writing mg over cosine theta. Now, copying everything else, sine theta, mv squared over r, and now I can see mass cancels. Hey, there is sine theta over cosine theta. Can we replace that with something like t theta? Oh, tangent theta. Okay. So when you have banked motion like this is the standard equation you get, okay? So now, depending on what is given, what you want, you can use that and solve problems. So in this case, we are looking for V, means you bring this R here and take the square root, right? So V gonna be just RG tangent theta. What if you want theta? You can still get theta from here. Solve for theta. Move G on the other side, okay? I think that's another problem we have, right? So I'll let you finish this first. So I'm gonna erase this because there is another question right there, I think. So for the circular motion, this equation comes out handy. G tan theta is V square over R for the banked card, okay? So how? Let's take a look. In this case, basically these two problems are same problem. Only difference is in the first problem, the angle is given and we are asked to find speed. In this problem, speed is given and you are asked to find angle. So it's the same problem, means we can use this and solve for theta, means tangent theta is V square over RG. This means theta is so what angle are we getting? Usually these angles are a small angle. Make sure your calculator is in degree mode in this when you are solving like this. Maybe it's a good time to take a break. Let's take a break. So in the chat, I see 11.5, 12. It's the same, right? So here, this question is in 2 sig fig. Maybe 12 is the correct way to write it. Okay, so now it's recording. Okay, so normal force down, mg is down. That means net force is sum of those two, assuming down as a positive, and we can choose down, up, left, right, anything positive for our convenience, right? And mass times acceleration, and acceleration is also down, means positive here, right? So that's that. So that while using on the top. So depending on what you're looking for, you can solve for that quantity. Now at the bottom, how is it going to change? mg is always vertically down, but normal force now going to be up, and acceleration going to be up. So we can choose up as a positive when we're using this at this point at the bottom. And let's say speed is v bottom or vb. Okay. So now sum of the force, see, normal being up and up being positive, normal is positive. mg opposite means negative. And acceleration is up means positive here. So now, can you make free body diagram on the side? Let's say here at this point. Can you make free body diagram? How many forces? 1, 2, 3. Can you type that in the chat? At that point, how many forces? 2 forces. Okay, which way is the normal force? Left, up, down, towards the center, or left? Yes, towards the center is going to be better, right? Your left and my left may be different. Okay, so at that point, normal force is this way, and weight is vertically down. So now, how do I use Newton's second law? Sum of forces towards the center. So acceleration is in this direction, right? So let's say that's positive. So sum of forces in that direction is mass times acceleration in that direction. And now there is only one force towards the center because the mg is 90 degree, means it doesn't have component in that direction. So just one force. Oh, that's just like a rotor ride looks like, except friction is negligible in this case. mv, let's say side square over r. That's it. It's the easiest one. So normal force is different at different points. Even if speed is same, normal force is going to be different at different points, as you can see. Okay. So now there is this video. I think it's from one of the commercial. Okay. So this guy is trying to run on the loop.
Tumbling, gymnastics and parkour. I'm attempting to run the loop because I've seen people do it on a skateboard before, I've seen people do it on a BMX before, but no one's ever tried it on their feet, so it'd be nice to be the first guy to actually run it. It looked a lot bigger than what I thought it was going to be. Yeah, I must admit, not the easiest thing I've ever done. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
basically boils down to the centripetal force. You need to keep on accelerating.
Does
So you need
that
to reach a
equate
certain
to
speed.
familiar?
And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour.
That it?
That's it.
Okay. 3, 2, 1, go. 17.
So they did quick calculation using the concept we've been learning and figure out, okay, you need to start with certain speed at the bottom so that you can pass through the loop, okay? And they are measuring the speed.
511. Easy 511. Can somebody show him that one back?
Well, this one's it. I know I've said that 3 times now, but this one is it. But I'm close. I reckon I'm close.
Getting close.
You can't really go any further until you take the match.
Chatting.
Yeah, let's get rid of. Let's go for it.
Okay, so you need to start with certain speed at the bottom so that you can just make through the loop. So next time you see the loop, measure the radius of the loop and also find out how fast you can run to begin with. And use that and see if you can make to that height. It is easier when we use this concept and conservation of energy concept together to do this kind of calculation. Conservation of energy, we're going to be talking about that in another chapter next week. Okay, so for this, I'm not doing that kind of calculation here. Okay, but here is this question for you for a situation where something is in the loop. Hey, I have a bucket just like that. Right? Do I have something that can go in the bucket? So now I need to find that, right? So I have this thing here that is there. And when I rotate this in vertical circle, at the top, what do we expect? If I don't catch it, we expect this to fall, right? But now, if I rotate it with at least certain speed, higher than certain speed, let's see. The ball is still inside. It's not just the ball. We can put water and can rotate, spin it without spilling the water. Where is my water bottle? Hope it doesn't go everywhere in my wire and it starts sparking. Okay. So, oops, I already spilled it. There is water. Did you notice it was spilling? I don't know how nicely you can see it. So I need to go a little faster to begin with, okay? So that's why I'm doing this, to set up the speed. So what happens? What's happening? Why water is not falling? The gravitational force is working on making it go in circle. So if something is sitting on bucket like that, there is a normal force. And I am reading applause. Thank you for that on the chat. So now let's try this. This ball here, right? Oh, this thing is kind of a bit hurting these days for some reason. Let's see if I can flip it and not drop it. Flip my hand and not drop. And if you guys have something, you can grab it that's not breakable, okay? Like this, and try this. Still there, see? I'm not catching it. It's there, it's open, right? And if I go fast enough, I can do it, okay? So all those forces are being used to go in that circle. So anyway, so now there is this question, folks. You have 2 minutes and 30 seconds. So if I were you, I'll draw the free body diagram for each of those spots. Remember, we talked about free body diagram. But object of interest is brick inside that bucket. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. Okay, we mostly got A and D, B, C. Okay, we have all. So here it says constant speed. So here, that speed, what does that speed provide? You know, where does that speed come from? Now I cannot spin this bucket. So that speed comes from, let's say in this case, that comes from the tension, the force I'm applying, right? But brick doesn't have tension, but normal force. So what happens? To get that speed, there are two forces working. normal and mg. Two forces providing it. Over here, what's happening? Only normal is providing that speed. Remember, only normal is acting towards the center. Over here, only normal. And here, normal has to even balance the mg. And only the difference can provide it. But over here, two of them are doing it. So looks like normal is doing hardest work over here. So that's, at this point, looks like normal gonna be the largest. Because normal had to balance the mg, and then rest of it had to provide the speed. Over here, normal is actually getting help from mg. Mg is also acting in the same direction, means both of them are providing the speed, okay? So it looks like normal has to do least work here. So that means value of normal has to be smallest at that point, okay? And that means that being the top, okay? So it looks like A is the correct answer in this case. But don't take my word for it, just write down the equation, okay? So for example, at the top, sum of forces, two forces, N plus mg, is mb square over r, means N is mb square over r minus mg. So if you are on the cart, let's say the roller coaster rider, and at the highest point, that's when you are feeling your weightlessness, okay, less weight. See what's happening here? The normal force, there is difference between those. If I come down here and write this similar equation, what do I get? N positive, but mg is negative, and that is providing same b square. So that means N is mb square over r plus mg. See, normal is large here. Normal is small. So for example, if mg was, let's say 8, and this mb square over 2 was 10, then that would be 10 minus 8, means just 2. If that was the same here, then that would be 10 plus 8, 18. See how they are different, okay? And over here, that would be just mb square over r. mg is not playing role on the side, okay? So anyway, so A is the correct answer in this case. So it helps always to make free body diagram and think from there. So yes, it's not easiest question, but it's doable though. Okay, so circular motion. So now let's look at the circular motion in big scale. Moon is going around the earth in a circular path. Earth is going around the sun in a circular path. So that means there must be a force. So the force that keeps these objects in a circular path is the gravitational force. See, there is nothing, no string there. It's not slipping on any, it's not sliding over any surface, no normal force. What is the force? It's the gravitational pull between two masses. So this idea was given by Newton. So that's why we also call this Newton's gravitational law, okay? So how much is the force? It depends on masses and how far the masses are. So farther the masses are, smaller the force. Actually, if we go from r to 2 times r, since in this formula we have r square, that means we need to square. Means we pick up a factor of 4 there. So this 4 gonna be down there if the distance doubles. So that means force becomes quarter. That's what this equation is telling us. If you just double one mass, the force is going to be double. If you double both mass, then force is going to be double times double means 4 times. So that's what this equation is telling you. Okay, and this G is just a constant, a number. Okay, so don't worry too much about that. So that's what it is saying. So larger the mass is, larger the force is. Farther the mass is, smaller the force is. Okay, now what happens? My hand here, one fist, let's say, has mass m1. Another fist has mass m2. So force between these two is m1 times m2 over r square times g. That r is this distance. So for larger object, we measure distance from the center. Okay, we measure distance from the center. That's what we do for the larger object. Now, there is force between us and the earth. Since we are at the surface of the earth, that does not mean we are at 0 distance from the earth. Since we measure distance from the center, that means we are at a distance, a radius equal to the radius of the earth. Okay, so that means how much force? One mass is going to be mass of the earth. Another mass is going to be our mass. If you are talking about force on you, that's going to be your mass. If I'm talking about force on me, then another mass is going to be my mass. So it could be anybody's mass or any object's mass. So let's just write m for now. But another mass is earth. We are talking about force between us and the earth. Okay, so now if I plug in these numbers, the radius of the earth here and the mass of the earth in one of the masses, another mass I'm just keeping m, and of course I need to put value of g as well, uppercase G. Looks like I didn't write that. And uppercase G is 6.67 10 to the power negative 11, if I remember correctly. Okay, so when we plug in those numbers, that's where this magic number 9.8 comes from. Product of that uppercase G, mass of the earth divided by square of the radius. This thing is 9.8. And that's what we've been calling lowercase g, acceleration due to gravity. Remember, force is mass times acceleration. And in this case, acceleration is 9.8. And we've been calling that 9.8 g. That's what that is.
I have a question really quick. Somebody typed in the group chat, does this only apply in space? And I think that the answer is it applies whenever you're comparing Earth with an Earth's gravity, Earth's force on another planet, right? It's not in space. It's not just in space. It has to be with Earth, correct?
It can be between any two masses.
Okay.
This and that. There is force between these two masses. Do I feel that? Do I feel that? I don't, because this mass is really, really tiny. When you are sitting next to another person, there is gravitational force of attraction between your mass and another person. But you don't feel it because when we calculate that force, it's very tiny.
Okay.
That turns out actually, if you calculate force between two persons standing 6 feet, social distancing distance. Okay, 1 meter. Oh, that's not 6. That's just 3 feet. 3 feet. Okay, 1 meter. You do the calculation. How much force you get? Force you would feel when you put a piece of apple. How big the piece? Cut an apple into million pieces. Can you do that? Let's say you can. Cut one apple, this medium-sized apple, into million pieces. And then put one piece in your hand. How much do you feel? Not much.
Yeah.
Okay? So that's gonna be the force between you and another person standing 1 meter apart. Approximately that. Okay? So that's very tiny. So that's why we don't feel that. That doesn't mean it's not there. Theoretically, yes, there is. Practically, it's not. So that means it applies everywhere, not just on the space. Anywhere, between any two mass. Okay? Between mass, let's say here and on the moon, there is. But what happens? That force becomes really, really small. Really, really small. Force between me and moon, there is that force. But that force is really, really small compared to the force between me and the earth. Okay? So yes, it's everywhere. It's everywhere. Somewhere it's larger, somewhere it is smaller.
Okay, thank you.
Okay, I'm glad you asked.
I have a question as well.
Yeah.
How did they figure out the mass of the Earth?
Yeah, how do they figure out mass of the earth? That's a good point. So let's see. There are a couple of ways we can do it, but for that, let's see. For example, if we can estimate radius of the earth. These days we can go around the earth, it's really easy. But we can even estimate the mass of other planets from here, radius, because if you are there, and let's say if you are there, sorry, and looking at this, you can actually measure this distance, right? And this angle, and calculate this. Theta is S over R kind of thingy. Think about this as a S, this as a R, so you can find the angle. Or if you, when you measure angle in radian, you can tell what the R is, this distance here. Oh, there is another way to estimate the distance. So anyway, so you can estimate the sizes, okay? So somehow if you can measure the radius, then you can actually, you know, what you can do is, this G here is this. G is GME over R square, radius of the earth, okay? So now you can rearrange this equation and solve for mass. Since you know G, you somehow have figured out, let's say, radius. You are in the earth, you should be able to find it, okay? Go around, that's a circumference. So you can find radius from there. So anyway, G is constant. So you can actually calculate that mass, estimate the mass. So there are different ways you can do it, okay? So yes, that's how they do it actually, using this gravitational formula.
Okay, cool, thank you.
Okay, I'm glad you asked. Okay, so our weight, we've been writing mg, gravitational pull, basically that's what that is, force of gravity on us, okay? And earth is pulling us and we are pulling the earth up at the same time. That's action and reaction there. Earth is pulling the moon, moon is pulling the earth. But earth has really large mass, so because of that, acceleration of earth is negligible. But moon has smaller mass, way smaller compared to the earth, so that's why moon is accelerating around the earth. If you hold hand of a kid, you can easily rotate the kid gonna go around you, and you're gonna just move in a very small circle because you have way larger mass than the kid's mass. Try doing that, spinning a portion of your mass. It's not gonna happen. You're gonna be going in a larger circle as well, okay? So anyway, so those are the things, okay? So your weight is just m times g, but your weight depends on this r, and this r being radius of the earth when we are at the earth. But once we go above the earth, what happens? This distance is not equal to, distance between us and earth is not equal to the radius of the earth. So the value of r increases means value of g decreases. So g is not fixed. It changes with height, okay? So I think that's what I talk here. So before we take, call the day off for today, so let's quickly vote on this. And you have a minute to answer this question.
Are we assuming that one mass is doubled?
Yeah, one mass is double mass. Another one is, yes.
Okay.
For some of you, you may find this tricky, so think hard, a bit harder, okay? 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So what did we get? See, it's a very interesting question. So let's recall the force. Where does the force come from? So one mass is m, another mass is 2m. And g and r square, we are not changing the distance, right? So this force is force of attraction between these two masses. See, it comes from both masses. How much force is there? It depends on mass, yes. But how much force is between two masses, one versus another one? These two are like action and reaction, just like I was saying. Moon and Earth, they exert same amount of force. I am pulling Earth up with the same amount of force Earth is pulling me down. Those are like action and reaction force, okay? So they are equal. And that force we are calculating by using both masses. So as long as these masses are fixed, see, there was m, 2m, 2m, m, they are same masses. So force must be same, okay? So B is the correct answer in this case, folks. So yes, kind of, it sometimes makes confusing, okay? So that's how we need to think. So that's why I bring this kind of question, okay? So let's leave it here. I'll see you guys next week. Have a nice weekend.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.